Okay, so the last lab is this week, so it will be due next week on Friday, April 23rd. You'll have another week to do it. Get signed off, get those in, and you'll be free of lab. The last pre-lecture is on Monday, and homework 12 is due on Wednesday. That's the last homework, and our final exam is going to be Monday, April 26th from 3 to 5 p.m. We'll just review for the final next week. So there won't be any new material, and that'll give us more time to stop and ask questions. We can review the first half of the class on Monday, the second half of the class on Wednesday. And so there'll be plenty of time for questions and all kinds of things like that. Your grade increasing opportunities, the course evaluation receipt is worth 5 points on the final exam. A lot of you have sent that, some of you have sent that in already, maybe about a third of you. Get it in, it's some free points, and also it kind of helps me out. Every once in a while, there's one kid in the class who's really ticked off at me and writes me a horrible review because I did something like gave him a B when he had an A test average, but didn't turn in any of his homeworks. And then they just tell me off. They just tell me off in the review. So having everybody in the class actually fill out the review helps me, because then there's not it mellows out the one kid who's ticked off at me. The practice final exam is posted to BB Learn along with the solution. It's worth 10 points on the final exam. It's for you to review. You can just copy the solution down if you want to. Do not print out my solution and turn that in as your practice final exam. And yes, that has happened. They crossed out the word key and wrote their name. It doesn't work like that. You do it, at least do it in your own right. It's for your benefit more so. It'll help you review everything that we've learned this semester, so you'll do better on the final exam. There's 21 bonus points on homework 12, and I will take 1 week of late lab for credit. It's only partial credit on multi-week labs. It will be a maximum of like 100 points. If you turn in lab 4 and you haven't turned in lab 4 at all, the highest grade you can get on it is 100 out of 300, because that will count as 1 week of lab. Still pull your grade up. It's better than a 0. Yes, it's open. I really pulled a trick. I don't know if they meant for it to be open or not, but it was in my teaching schedule. It was showing up on Louis. It just wasn't showing up for students to enroll. So I just emailed the scheduler and say, hey, look, you messed up this build. Can you just go ahead and allow the students to enroll without saying anything to anybody else? So students can actually enroll for $490 in the fall now. Last time I checked, there were 28 seats left. We need to get about 12 students to guarantee that they won't, the university won't go through and cut the enrollment. And I think that's usually fairly easy to do. It usually fills up. The prereq is EE280 with a C or better. Again, it's, if we go back to the normal route where people are actually coming into class, a lot of the class is me talking for 15, 20 minutes, and then you guys going out to the bench. Or I've got the other model where I just talk on Mondays, and then we work on the bench on Wednesdays and Fridays. And I will be there, and I know how to troubleshoot and figure out what's going wrong. So that will help you out. The only prereq on it is E280 with a C or better, and so you guys should be able to enroll. No, I won't. And we've talked about this. And the final exam is on 3 to 5. The Zoom exam will be at the same time. You can come in and take it in the building. It's a little bit more relaxed that way. You don't have to worry about the technology and all that stuff. So I will just do them both at the same time, just because the final exam schedule week schedule is kind of weird. 5 sheets of notes, and it covers everything from switching circuits to BJTs. Go through the practice final exam, the practice final, and the final review. The exam 1 and 2 review, That would be where I would focus the most. If there's something you really want to go back that you don't understand, go back to the homework and solutions and maybe even the lecture slides. And you can always ask me questions too. Generally, I'm in my office the entire week of finals week, except for when they keep scheduling lab meetings. I'm just not going to talk about that. I had 4 lab meetings this week. I start working May 1st. The university won't pay me until May 8th. So I'm planning on taking like a week off somewhere in there and just calling it good. Yeah, keep your attitude up. We're almost done. That's the first transistor. And let's go into actually designing a BJT amplifier and what goes into that. Let's see who that is. John. Okay. So what do we got going on here? Oh, this is just an introduction slide. Oh, great. BJT amplifiers. Sorry. Oh, you were already here. Yep. Okay. Let's go back to that. So we've got different operating regions here. Just like it looks an awful lot like a MOSFET, but this one's called cutoff, which is a normal word for it. The one where we're actually using amplification for our linear circuits, for our analog circuits, is called the active region. And down here we have triode. No, not triode. Saturation. Sorry. Names confuse me too sometimes. Okay. If I put in the region where it's slopey, and notice the slope is steeper for a BJT, they have higher gain. If I put a small signal across at a DC value right here, plus some small signal, I can bias it up in this region where I have slope, and I have a small, my minimum signal here is going to correspond to this axis. My maximum signal here is going to correspond to that axis, and I have a much bigger signal on the output than I put in at the input. Okay. So we call it a common emitter amplifier. The input signal's coming in on the base. The output signal is coming out here, VCE, on the collector. And the emitter is grounded. It's an AC ground as well as a DC ground in this case. So the emitter is common, it's grounded. That's why they call it a common emitter amplifier. Now, just like we did for the MOSFET, we know that IR, the current through, which is IC in this case, will also equal IC because they're in series. We can use Ohm's law to find IR. It's the voltage drop across the resistor, VCE minus VCC minus VCE, what I wrote, not what I said. I know I didn't freeze. All divided by RC. We've been given this equation for a BJT, the characteristic equation for the current, IC equals IS E to the VBE over VT. And VT is KT over Q, it's about 25 millivolts. Since they're both equations for IC, we can equate these two equations and solve for VCE, and we get an equation for VCE as VCC minus RC IS VBE over VT. If we want to find the voltage gain, it's always defined as the rate of change of V out with respect to VN. My output voltage is VCE. My input voltage is VBE, so I can make that change right there. And I can take this equation right here and take the derivative of that with respect to VBE. The VCC will go away when I take the derivative. The RCIS will come out along with the negative sign. The derivative of e to the VBE over VT with respect to VBE is going to be e to the VBE over VT divided by the derivative of this, which is 1 over VT. So I get that expression for the gain. And I notice that this piece right here, IS e to the VBE over VT, is just my IC. So I can write that as RC IC over VT. Okay. Now, what do we want to do here? We've got IC is 1 milliamp. Oh, that doesn't matter, Dr. Brower. VCC is 5 volts. We want to have the maximum symmetrical swing. So when my AC and DC together, I've got a signal that looks like this. Let me draw this because I kind of do this and I don't think people understand what I'm doing. So this is my signal on the output, VCE. It's got a DC part, but when I add AC to it, the voltage can go up and down. So the absolute maximum voltage I can get out of this before my transistor shuts down, and right as the current goes to 0, yes, good. Okay, that's fine. I just take roll and worry about it later. Oh, good. And I checked you off. Okay, and if you email me later, I will give you credit for being here. So if I cut IC to 0, the highest voltage I can possibly get at this point right here is 5 volts. Okay, now this bottom value right here, I have to keep the transistor in the active region. And we know that when it goes into saturation, VCE sat is around 0.2 of a volt. So if I want to keep it out of saturation, my ballpark thing that I use for this class is we're going to have VCE minimum in active. We'll just call it 0.3 of a volt. These are very ballpark calculations I'm doing here because everything depends upon beta. And beta changes wildly from transistor to transistor in the bin. So these are approximate calculations. So my VCE min here is going to be around 0.3 of a volt. Now, what did I want to say? Maximum, what's the question? I don't know what the question is. Let me look at my notes. Part 2, number C. What did I do? Oh, I wanted to calculate the gain. So what we're going to do is we want to set this so our VCE is smack dab in the middle of those two. And then I can have the most swing on the top as I can have on the bottom. So the 5 plus the midpoint of 5 and 0.3 is 2.65 volts. So the midpoint between max and min is going to be 2.65 volts, halfway between 0.3 and 5. So we set our DC operating point here at 2.65 volts. Then I know what my, I was given what my IC was. We can calculate RC. RC, V equals IR, so it's V over I. VCC minus VCE over I. So 5 minus 2.65. Did I do that right? That is an amazing thing. I have no idea. Oh, I didn't even do this before. Over 1 milliamp. Calculator. It'll also come out in K ohms. 5 minus 2.65 divided by 1 is 2.35 K ohms. So we could get a value of R, 2.35 K ohms. We could calculate the voltage gain. AV is minus RC IC over VT, 2.35 K times 1 milli over 25 milli. I'm using this stupid calculator. 2.35 times 1 divided by 25 equal 2.35 divided by 25 gives me, and multiplied by 1,000, that'll give me 94. Remember, there's a minus sign there. So the voltage gain is a little bit higher than what we were typically seeing with those MOSFETs. They've got higher gain and they have higher bandwidth. Okay. So we want to be able to actually go through and do this small signal model. We figured out the voltage gain. It's the rate, it's V out over Vn for that particular circuit is minus, what the heck was it? I wrote it down, RCIC over VT minus RCIC over VT. Generally, if I want to do this, and I want a really good, know what the voltage gain is, I build it and I measure it because there's a lot of variability in these devices. I can measure beta for the transistor and then I can simulate it. But if I don't know the beta for that particular transistor, I'm in trouble. If I'm doing this in production, I figure out what's the gain going to be at small beta, what's the gain going to be at high beta, what's the gain going to be at the middle beta, and I just have to set it so that it's always acceptable. Trickier than it sounds. Notebooks this thick, full of calculations. But they're mainly repetitive calculations, so it wasn't that bad. We need to apply this to the transistor model. We've got to find the change in IC with respect to VBE. Well, that's going to come from this equation. So I take the derivative of this equation, what I get is I actually get the old value of IC over VT. And this is defined as GM. So we're going to do just like we did in the MOSFET. Our GM is a change in IC. So this is a dependent source with respect to VBE. So this is going to be GM times little VBE. This is an AC model. And this is little VBE. We have a new component in here because we actually do have base current. We have to find the rate of change of IB with respect to VBE. Well, IB is just IC over beta. So it's IB is IS e to the VBE over VT divided by beta. What we get there is we get a resistance value. Now, this is like a conductance. So when we do that derivative, we get VBE over IB, which is also beta over GM, which is also VT over IB. And this value is called R pi. Forget the double R. I just edited this today. So I put R pi right here. It's a change in IB with respect to VBE. So that's just a resistor right there. And that is, yeah, it's 1 over that derivative. So we've got, this is our basic circuit model. It's called the hybrid pi model. I don't know why that resistor was named R pi. I really don't. This was back before my day. This was when my dad was in college in the 40s. That they came up with these names. And he was a chemical engineer, so he doesn't know this stuff. Knows a little bit of it. Transistors were the modern new hot technology then. So when we design these, what we're going to do is we've got this basic circuit model here. We can stick into our circuit, our AC circuit, and then we can do some circuit analysis on it. And we can do different types of circuits and not just the one we calculated, we derived this gain equation for. So this is a more general purpose way. So step 1, you draw the DC circuit. We have to deactivate the AC sources and get rid of and the capacitors become opens. And once we get that DC circuit, we use it to find the DC value of IC, VBE, and VCE. We can verify it's in the right operating region, and we can calculate R pi and GM, and also it has an RO2, but we haven't talked about it yet. So we can calculate 3 values and get the small signal model. RO is going to end up right here, where it was in the old model, RO. So we calculate those, then we draw the AC circuit, making sure we put that small signal model in there. And I'm actually using this less and less. And then use that to calculate the gain. V out over Vn, VCE over VBE. So this is a very general introduction. If you want to know the gory details, it's in the Cedra-Smith book. The 8th edition actually interleave the BJTs and MOSFETs, so you can see the similarities between the common source and the common emitter amplifier. The 7th and the 6th edition puts these in separate chapters. I also have the 1st edition of Cedra-Smith in my office. That's what I used when I was in college, back in the dark ages, 1980s. So what we want to do here, we want to...
Sorry, can you go back for just a quick second?
Sure. Oh no, it's pizza night. I gotta get out of here and I've got to go in the IEEE room and see.
Okay, thanks.
Okay. My food for pizza night is in the refrigerator. Okay, so this is the part where we want to draw the DC circuit. DC circuit. This is my DC analysis. Somebody's chatting at me. How did I get 2.65 volts? What I did is I had 5 volts was my maximum voltage, 3 volts was my minimum, 0.3 volts was my minimum voltage, and I found the midpoint between 5 and 0.3, which will be, did I get that right? No, I didn't. I'm slightly off. Let's go back and recalculate that. It wasn't 2.65 volts. We can calculate that somewhere in here. The midpoint between 5 and 0.3 would be 4.7 over 2. The difference between the two of them over 2, that's just the average of those two thingy. Well, that'd be 5.3 over 2. The difference between the two of them, it's not the average, it's the difference between the two of them plus the minimum value, 0.3. And I did that in my head, so I probably got it wrong because my calculator is sitting 5 feet away from me and I'm too lazy to get over there and get it. 4.7, and I'm using my phone, believe it or not, 2.35. Oh, I did get it right. Plus 0.3 is 2.65. So it's just the midpoint between the minimum and the maximum is where I picked the bias point to be. That will give you the best linearity, and it will give you the highest level of signal swing on the device. Where are we at? We're right about here. Believe it or not, we're gonna get done early today. It's the end of the semester. We had extra days because there were fewer tests. Okay, so the DC circuit, we're going to deactivate the AC sources. And when I deactivate the AC sources, what I get is they just go away. It becomes a short. So I basically 0 volts across that AC source. I don't have any capacitors in here, and that's the only AC source I have. So that is my DC circuit right there. Now we're assuming beta equals 100, and I've already told you that's a big assumption. We're assuming it's already biased up in active mode, that we actually check that. We may go back and do that. We want to figure out what the voltages and currents are. Well, the first thing I know is that if it's in active mode, VBE has got to be 0.7 volts. If it was in sat, I could also add VCE equals 0.2, but if the transistor's on, I have to forward bias the base emitter junction. So I got 0.7 of a volt across here. This is at 0 volts, and if I go 0.7 of a volt above 0 volts, this side of the resistor must also be at 0.7 volts. And I can use that to calculate IB, because we know what the DC value of the base voltage is. So the voltage drop across RBB is going to be 3 volts minus 0.7 volts. V equals IR. We got R, so we want I. My R is 100 K ohms. And when I do that calculation, I'm going to get IB. This is big IB. And that should come out to be 4 is 23 microamps. And I got that just by knowing the transistor was on. So we need to get IC. So IC is beta times IB. So it's 100 times 23 microamps, which should be 2.3 milliamps. Okay, we got that one. We know what VB is because we assumed it was in active mode. We got number 2 or number 3. We got IC. And we need to find VCE. So we've got the collector current. We just calculated that. 2.3 milliamps. I can use Ohm's law on RC. And I know that VCC minus VCE is the voltage drop across RC, and that will equal IC RC. And we've got RC, we've got everything but VCE. So VC, when I do a little bit of algebra, I get VCE equals VCC minus ICRC. And that is 10 minus 2.3 milli times 3K. And I actually did this. VC, which equals VCE, which is the same thing as 3.1 volts. Now we want to go through and check and make sure it's active. So to be inactive, I've got to have VB equals 0.7 volts. We assume that to start out with. We've got to check VCE. Active. We want that greater than like, which is just VC minus VE. We calculated we calculated VCE. Never mind, it's the same. VC and VCE are the same thing in this problem. VCE is 3.1 volts. That is greater than 0.2 volts, so we are active. We're not in saturation. We need VCE greater than 0.2 volts to be active. Okay. And we talk about in my old school, we'd actually talk about this, and then we'd build these circuits in the lab because there's training them more to be technicians. So most of the class was actually them building stuff in the lab. Another thing that 490 in the fall comes from. And what they would notice is that their measured values were off by 20% from what their calculations were. And all I could say is it's a BJT. You don't know what beta is. It's the way of the BJTs. They're fast, but they are not quite as quality controlled. No one, I don't think anybody, nobody's figured out how to control beta. Okay, so we've gotten the DC analysis. So our next step is to go through, we figured out VCE, IC, and VBE, and beta, and all that good stuff was given. We want to calculate GM and R pi. So I've got a formula for GM. GM is the DC value of IC, big IC, over VT. So IC, what did I use? IC was 2.3 milliamps. I'm looking at my solutions to see what number I used here. I used 25.9 millivolts for VT. Always check the front of your exam or your homework assignment to verify it hasn't been changed. That's another thing. All these parameters vary with temperature. On a warm day in Phoenix, you get a bigger VT, you get lower gain. 88.8 milliohms. If you're lucky enough to live in Saskatchewan, your transistors have really good gain. R pi, sorry, I'm talking a lot to my Canadian friends lately. We want to calculate that. I use beta over GM. You can use any form of this equation that you want to. We approximated VBE, so I'm not going to use that one. I'm beta over GM, 100 over 88.8 millimos. And a mo is 1 over an ohm. If you didn't have 188 with me, which is really probably more likely, a mo is 1 over an ohm. So an ohm is V equals IR. It is a volt per amp. A mo is an amp per volt. If you're keeping track of your units. R pi, what the heck does that come out to be? This is number 5. 1.13 k ohms. They don't have very good input resistance. Sorry. That should be said in the next class. Lower input resistance than a MOSFET. Okay. We've got GM and R pi. We want to draw the small signal circuit now. We're going to deactivate the DC sources. So this one goes away. VCC gets shorted out, so that goes to ground. And we want to draw the small signal circuit. Don't skip this step because this is just like how we figure everything out. We have the base. We have R pi, 1.13K. We have the emitter. My VBE is the voltage across here. I have that little dependent source. GM, we got a number for that, 88.8 milli times whatever VBE was. And we haven't put R out in here yet, so we'll just leave it like that. And this is the collector. What do we do here? We look at how our circuit's connected. So this, what I've drawn here is this little, these two pictures are equivalent. I've drawn a model of the transistor. I just got to check and see where all the base emitter and collector are connected. The emitter here is connected directly to ground. So I'm going to connect the emitter to ground. The base sees 100 k ohm back to my AC source. So 100 k ohm in series with the AC source, VN. Okay, 100K. I drew this too big. I'm going to run out of space. On the collector, I see RC, which is 3 k ohms tied directly to ground. So 3K to ground. Now notice here, this is tied to the dependent source is tied to ground through the emitter. The resistor is tied to ground through the deactivated DC source. So these two are actually tied together. So I can continue that line if I want to. I want to divide this circuit into two parts. Yeah, that's good. I'm going to look at this front end and solve for VBE in terms of VI. If I get VBE over VI, yeah, that's right, and I get, this is my V out, and I get V out over VBE, and I multiply those two together, the VBEs cancel, I actually get the gain. So we're going to divide it into two parts, calculate each one of those, and not worry about what the input voltage is. The input voltage is going to vary with time and temperature and which part got built into that particular device. So we're just going to set up the gain for this, and then we can draw, the goal of this is if we can calculate the gain of this, and you also need to know the input resistance and output resistance. We'll talk about that in 380. You can take this whole transistor circuit and replace it with a triangle and say, this is an amplifier that has this gain, it has this input resistance and this output resistance, and then put it in a signal chain with a whole bunch of other stuff and do calculations on that without thinking about the details of this circuit. So that'll be the higher level model of this amplifier. What I do in 380. So for this orange thing that I've got circled here, this is just a voltage divider. So my VBE is going to equal VN, my input voltage, times the resistor I want the voltage across, that's the 1.13K, over the sum of the two. Okay, we've done a horrible thing here, haven't we? Yep. What we find is VBE over VN. When I calculate that, that's this thingy right here. It is 11.7, 11.17 times 10 to the minus 3 volts per volt. Because this resistance is so low, I would need a very small resistance source to get anything on this front end. It's not very good. What could possibly save us here? Okay, change colors. green. We want to look at this piece of the circuit right here. And this is just a current source going into a resistor. So I've got V equals IR. Notice the current source is actually going into the negative side of the resistor. So the voltage at the output is going to be negative. So I calculate V out over VBE. Wait, let's do it this way. V out equals the negative of the current source, 88.3 milli, that looks pretty small, times VBE times 3K. And so I move the VBE over to the other side and I multiply these two together. I basically get V out over VN, I'm running out of space, is negative 266.4. Is this enough to save us? Volts per volt. I multiply these two together. Up here, I'm just running out of space all over the place. And the answer comes out to be negative 2.98. How could we improve that? We could make RC bigger. If I make RC 30K, my gain's 29. That's easy enough to do. A bigger resistance will be lower current. I could lower this. This is what's killing us. But you generally don't want to have a big resistor there because then you have big base current. And then I would get a better signal on the output. That's what you get to do in the homework. What do we got here? Locate. Oh, yeah, good. Oh, yeah, just stop.
So you're saying at the bottom on the left side, in the
Yeah.
green, V
Yeah.
naught over VI equals negative 266.4 volts per volt. But
Yes.
I'm just kind of like wondering why, on the other hand, you have V naught over VI in orange equals negative 2.9 volts per volt.
2.98, because what I did is I took, this is, oh, that's V out over, sorry, that's V out over VN. I did that wrong. That's V out over VBE. Thank you for catching me on that. Because when I did that voltage divider, oh, and this is just like complete. So when I did that voltage divider, this was V out equals VBE on this side. So that really should have been V out over VBE. Thank you. You can read that. And then I multiplied the two values I had together, V out over VBE times VBE over VN, and I still have some gain.
Cool.
We could make it bigger by playing with our resistances. Probably the easiest one to change is the 3K. I don't want to make RBV much smaller because then I have other problems. So we're locating the bias point. We've already kind of gone through this a little bit. VCC is 5 volts. That is going to be my VCE max. I cannot get a higher voltage out of the circuit than that. The minimum voltage I can get out of this and keep it in active mode is around 0.3. If I go down to 0.2 volts, I will be in saturation mode. So if you think about this graphically, when VCC is 5 volts, I'm right here. When my VCE, this is the VCE axis, I'm at VCC, I'm pretty much in cutoff. And you're biasing this all the way to the edge of cutoff when I'm right here. This is VCE max. My minimum value of VCE is to keep it out of saturation is right there, VCE min. If I want to get the most signal swing, where I want to put this is I want to put it right in the middle between VCE max and VCE min, and then I can get the biggest signal swing out of this without cutting the transistor off. I could get signal swings all the way up in this range. That would be my maximum signal swing. And I will get the biggest signal swing when I put the Q point, the DC operating point, right in the middle. My AC can add to that DC point, and it can subtract from that DC point, but I will get the maximum signal swing right there. Now, we put it in the middle, and we've already agreed that is 2.65 volts. Halfway between 5 and 0.3. I'm going to do some erasing thingies. Now let's say we don't need this full 4.7 volt swing. We only need plus and minus 1 volt swing. I could move this Q point all the way up until, what color? Oh, I'm on eraser. That's why. I could move this Q point all the way up to 1 volt less than the max. And then I could still get 1 volt of signal swing on the top. And I could move it down within, this is my DC bias point, within 1 point of throwing it into saturation, 1 volt of throwing it into saturation. So I've got this whole other range of Q points I could choose. Now there's a good way to choose that point and there's a bad way to choose that point. Probably the best thing you want here is if I only need a plus or minus 1 volt signal swing, you want to move the Q point up. This is a good thing to do because what does this do to you? I get closer to cutoff, I lower the current, I get lower power dissipation, which makes you a hero if you're in a battery operated system like a cell phone, or if you're just in a system where you care about the heat dissipation in the system because you don't want to melt things. Lower current is always good. So if I have a choice, I'm going to move the operating point up from this Q point. Won't get quite as good linearity, but I will get a lot lower current. Now, if I'm crazy or I don't know what I'm doing, I might move this Q point down this way. What happens down here? I have higher current and I have bad linearity because I've made this thing stops looking like a straight line. It's not going to behave as well. So I've got the worst of both possible worlds by moving this Q point down. So you just don't do that. Where you want to operate is from this middle point to upwards. This Q point right there gives you the best linearity. A Q point up here gives you the lowest current. And it's always a trade-off. Your boss starts yelling at you because the battery only lasts for 43 minutes and they really want to advertise that it lasts for 40. This is a true story. They really just want to advertise that it lasts for 45 minutes. How much can you drop the current on your amplifier? And you're sitting there going, none. We're at the hairy edge right now. Well, what else can you do? Well, this is when we go through the whole, it turns out, nobody should tell you this. If we were using NiCad batteries. If you take a NiCad battery and you fully discharge it, like overnight, just drain power out of it till you get every ounce of juice out of this thing you possibly can. Just tie it to a resistor and leave it overnight. And then you come in the next morning and you take this battery and you throw it into a freezer and you charge it in the freezer, guess what? You get 45 minutes out of the day. We did it. We spec'd it. It was really more like about 43. I had data to back that up. Yeah, allergies. Okay, one thing we have not talked about yet, and we're almost done, is this it's base width modulation is like the channel length modulation. It's a change in IC with respect to VCE. So we've already put these two thingies in our model, our pi and GM VBE, where this is our little VBE. And we want to put something else in there. A change in IC with respect to the voltage between C and E, that looks like a resistor. And we call that little RO. We calculate that by doing the derivative of this. This is defined as little RO. When we do we use this equation, we take the derivative of it. We come up with IC, this value right here, divided by the early voltage. I flip it over, I get the actual value of RO. RO is the early voltage divided by IC. The way we get the early voltage is we measure it. We look at these transistor curves, we take the slope of the line in the active region, and we draw an imaginary line back to the x-intercept of that line. And I do that for a whole bunch of curves, and they all converge on a point, and that's minus the early voltage. So this is actually modeling the slope of this in the active region. It's not a real resistor, but we can throw that in that model, and we have a complete BJT model. And I think this is the best I've done BJTs in about 8 years. But we are done with all the new material for this course. And it wasn't that bad. It came out of the first time I taught this class. And I was talking to somebody who was actually in that class. And I mean, I was terrified because I actually had to teach this with algebra, not the way I was used to teaching it to the technicians, where it was just like, okay, here's an equation, just use this. Here's an equation, we'll go measure it. And I had to learn Laplace transforms and actually get them right as compared to when I did that back in college. And I kept on, every time I got done with something, okay, we got it, it's not that bad. And I probably said that like 5 times every class. 380, you got to stay on top of 380 because it's cumulative the whole semester. It kind of goes through, and we use stuff from the beginning all the way along. It's a lot of work, but it's kind of what people think electrical engineers do, and what a lot of engineering is based on in Arizona. Our big industries here, 2 things for electrical engineer. Well, there's power. There's semiconductors, and that they're hiring all kinds of people right now because of TSMC coming down. And there's also some RF work. It's easier to get you to the point where you can have a semiconductor job with the NA curriculum than it is an RF job. But there's been some highly motivated people I've gotten there. It takes some extra work on your part. Talk to me if you're really interested in designing radios. 490 in the fall. It's a good hands-on class. You'll get back on the bench. You'll be able, I kind of treat you like you're a pup engineer and I'm the senior engineer. I'm deliberately vague, but I'm willing to help you out. It's more work on my part, but I enjoy it. And we are done. So any questions, any leftover stuff? Sign up for 490 so I don't have to teach what 88. And then once we get 490 filled up in the fall, we'll work on 490 in the spring. We'll start a new campaign. I'm gonna have to, oh, who am I gonna get? Okay. Well,
Hey, Ms. Julie.
Yes,
I want to ask you, does this class, the 490, count as major elective?
it counts as a major elective.
Okay, thank you so much.
Okay. Oh, let's see who I don't have here. Ibrahim Mubarak, Austin Arnis, Lauren, Jared Mountain, Jordan Ramirez, and Tyler Shepard. Yell at me or send me an email telling me you were actually here or that you watched the video. Okay, pizza night.
Did somebody say like they have one of their, like they're gonna take 490 and one of their classes is kind of overlapping the other? Did you say
Yeah,
that?
it's the 310 lab overlaps it by about 10 minutes. If you can finish your 310 lab early or spend some extra time on your 310 lab some other time, if you're willing to tell me you'll do that, I will sign the course, whatchamacallit, the course time conflict override. I don't actually have to sign the form, I just have to send an email to your advisor.
Okay.
Okay.
What if it was for 348?
I don't know what the times are. You'd have to check how much of a time overlap
It
there
would
is.
probably be the same thing as 310.
Yeah. Okay, if it's the same thing on the lab, then we just let me know and I will do that one too.
Okay. All right.
Okay. I forgot to bring them. Yes. They're in my office. If you want to walk over there with me, I can do them. Okay, good. Yeah. They were better than the first exam. Okay. Yeah. And most people, if they improve their grade or just their grades, basically stay the same. There wasn't anybody who dropped significantly.
Well, less material than the first exam.
Yeah, there's a lot of math on that first exam.
Yeah, I think that's the killer for everybody.
Yeah, and I don't care so much.